Okay, we'll start the session now. So today is that officially that last session for the course of biostatistic and design of experiment, and this is the 8th week, and hopefully one more session will be there. That will be extra session on Sunday. Uh, that might be I'll be discussing or I'll be just briefing from full total 8-week course that what we have done, and then we'll brief you. That will be on Sunday 3 to 5. Hopefully you will get all mail regarding that. And for 8 week course, that's the last session today. And today's session we will discuss about some of the design experiment method, like some we have discussed factorial design and then other factorial design or other fractional factorial design. So we'll discuss some other type of methods like uh, that Patrick is there, then Latin is there. Just I'll brief you, and then after we'll start. Before starting to that other experiment design, we'll discuss some that last class that some alias and then compounding was there. That today I will just try to clear with that, and I will show you with the example also. Then let's just start the regression. In the regression, we'll do that fitting of the line. We'll try to find out the slope of that. We have the data we'll be having. That two-dimensional data will be there. We'll find out the slope, then interception. Then we have to find out that correlation coefficient. Then we one more thing we have to find out that R square value or either that Sparkman correlation coefficient. Then we will do the fitting. That fitting we will do with the help of least square method. As of now, we'll do. Once we'll finish up that, then we'll in the last we'll discuss the control chart. What are the control charts is there? Control chart for the variable, control chart for the attributes, and so by that, so we'll be able to finish the session. So can anyone say that my voice is audible and screen? Mm-hmm. Hopefully that my voice and screens are okay. Okay, we'll go ahead. So last class what we were discussing, like we have discussed first fractional design. In the fractional design, what was that? We have to in terms of 2 to the power k. Okay, so let's say we have a number of factor is bit more like 7, 8. So we have to go with the 7 number factor or the 8 number factor. So number of experiment will be more. Just 1 minute. So number of experiment that is going to be increased. Let's say we have a 2 to the power 7, that will be 2 to 4, 4, 8, 16, 16, 32, 30, 64, then 128. And it will go, so it will go 256. So it's like it's just going more and more. That is not feasible to do that for all factor and do the experiment for all factor. So what we are doing? We are doing the fractional factorial design. Either factorial design, or we are saying in terms of what we can say screening method, or if we come to the next part, that's a roughness smoothing method. So in that what we are doing, we are whatever that unnecessary or unwanted variation or the factor that is there, that we are going to remove it. That what we are doing, the k to the power minus p, or either we are doing -1 of that. So that depends upon that what we are compounding or that what we are doing the aliasing. So usually what happening, it is often impossible to run all the observation in a 2 to the power k factorial design. Design under either that will be the constant or either that homogeneous condition. Because just 1 minute. Okay, so If the number of factors is continuously increasing, so our number of experiment will going to increase. It's because we have the formula for the to the power k. So, for example, it might be not possible to conduct all the tests on the one shift, or either that use of material will be single batch. Like if you are doing for the same testing, same factor for that we are going to repeat the experiment for different experiment for different factors. So maybe that the material wastage will be more. So in that, what we are going to do, we are going to remove the unwanted variation, and then we are going to do fractional. For that, we are doing the blocking and then confounding method. So for fractional itself, either we are doing the blocking and confounding. What do you mean by blocking? Anyone have the idea? Blocking. So when this problem occurs, like that is not feasible, to blocking is an excellent technique for the eliminating the unwanted variation that could be caused by the non-homogeneous condition. Let's say we have, I want to do the blocking. We have some group of data is are there. Initially, that data will be like it's not what we can say classified, or either the classification has been not done. It's random. Like 100 number of data are there. In there, men, the female are there, and they have defined in the age group also. In that male itself, age group will be there. Female also, age group is there. So now what we can do in the blocking, so first we can block male for that one particular group of A1, that age group of 1. So that will be one. Then age group of 2. So that will be that we are going to block for that one block, two block. Then for female, age group of 1, age group of 2. So that will be third block. That will be fourth block. So now we are just classifying the data, so that if the earlier it was, let's say we were having some different like factors were there, but now they will be, that factor will going to comes into the one, that for male that one factor is there, female one factor, so it become two only. Earlier male, female, age, and then age group also vary. It was okay. So just 1 minute, I'll accept the request. Okay, so in that, what we can do, like we can just club it and then we can do the blocking, so that number of factors is going to reduce out. It's, let's say it was earlier 4, it become 3. So 2 minus 4. So earlier we have to do for the 16. Now effectively we have to do for the 8 only. 8 number of experiments, that we know the design matrix for the 8 variables, or either 8 number of experiment. Okay. So if the design is replicated and if the block is of sufficient size, it's again like let's say I'm saying in the male itself we have a different group. So male age group like this, male age group, so that we can put in the one block. Okay, and then let's say we have a sufficient size. So then one approach is to run each replicate in one block set of, like it's a same condition. Homogeneous means it's going to be a same condition or same parameter. So we can do the blocking also. Let's say we have a example, we have 2 to the power 3 design, means like we have a 3 factor. So that is to be replicated twice. Suppose that it take 1 hour to complete each run. Like total we have to do the 8 run or number of experiment. Then by running 8 runs from the replicate 1 on one day and the 8 run from the second replicate on another day. So any time effect or difference between the how process work on the day 2 can be eliminated. What do you mean? Like this line they are saying, like when we are running 8 run from replicate 1 on one day and the 8 run from the second replicate on the another day. So any time effect or difference between how the process is going to work on 2 days. So it's like some sort of unwanted variation that is coming, so that can be eliminated. So in that way, so these 2 days become the two blocks in the design. Let's say in one day they have done for the 4 hour, second day the 4 hour, but we are just removing the unwanted effect, maybe the difference or either maybe time effect. So the average difference between the responses on the 2 days is the block effect. So what are the effect that is going to come? Okay, so what are the effect that is going to come? The average difference between the responses on the 2 days is the block effect. So overall effect, let's say in the first day we have run, second day run. So second day some sort of changes will be there. Maybe the time effect will be there, or maybe some sort of process effect will be there. So if you are going to take the difference, so they are going to collectively for the block effect, and that we can keep at one block. Then that the same way you can do for the another one. So it's like a blocking. It's nothing is there. It's just I am saying like let's say you have a. I will take one example. Like we have a drug, we have to administer the people, maybe that different age group of people. So we have a different variety of that. We can one block we have 100 people. So in the packet will be like so in one block we can keep the 5 to 10 year, block 2 10 to 20 or maybe 30, maybe we can keep it 20 till teen, and then block 3 we can keep to 20 to 50, that will be your adult age, and the block 4 you can keep that senior citizen or other old age. So it's like just we are doing the grouping in that blocking. Let's say we have A, B, C, D. If we take alone, so that will 4 again. If we take the interaction of A, B, A, C, A, D, and then again it will come A, B, C, and A, C, D, and the thing it will go till we will be having A, B, C, D. But the thing is that whenever that effect, when we are going to consider all effect, like the individual effect, it will be more high. When you consider going to take the interaction, it will be less effective. So we will try to remove by A, B, C, D, that we can keep I is equal to A, B, C, or either D is equal to A, B, C. So it's that effect we are saying the aliasing or confounding effect. So that's how we have to reduce the number of experiments or number of runs, so that will be easy to conduct the experiment. We don't want to do the experiment for the like long time. That will be a loss of resources and the loss of the time will be there. Sometimes we'll be not able to do the replication, or either will not able to do that, what we can say, uh, will not able to do the blocking in homogeneous condition. So in that, so we are doing the confounding effect, confounding design technique for the running a factorial experiment in block where the block size is smaller than the number of run in one complete replicate. Okay, so this case the confounding will do where the block size is smaller than the number of runs in one complete replicate. So actually this technique causes certain interaction to be indistinguishable from the confounded with the block. Let's say I have told like you have A, B, C, D, E, F, G, H, like some 8 or 9 effect will be there. So that need to be confounded with the higher order interaction. So that we need to indistinguishable that. Okay, so that technique causes certain interaction to be indistinguishable from confounded within the blocks. Let's say we'll take some example. We will that illustrate the confounding in the 2k factorial design in 2 to the power p blocks, where p is equal to less than k. What do you mean p less than k? So k is our number of factor. Now the p will be like the thing that I want to confound itself. That will be always, let's say 2 to the power 4 minus 2, or either 2 to the power 4 minus 1. So in that case, that matrix I will design design the resolution, then design generator we will discuss further. Let's say we want to consider 2 to the power 2 design. Suppose that, so 2 to the power 2 design will be having 4 run, 2 to the power 2 it will be 4 run. So requires 4 hours of laboratory analysis. That does 2 days are required to perform the experiment. If days are considered as a block, then we must assign 2 of the 4 runs to the each day. Means if we are going to consider the days, okay, so that should be going to consider as a block, then we must assign 2 of the 4 runs, like 2 of the 4 runs, like any that we have 1 run, 2 run, 3 run, 4 run. So 2 run, maybe this 1 2, maybe the 1 3, or maybe the 1 4, whatever, maybe the 2 3 also, whatever. So that run, that 4 runs to each day, either of that first run or 2 runs that can be done on one day, or maybe the first run or third run that can be done on one day, maybe the first or fourth, then 2 3 2 4, maybe then 3 4, that should be run on one day. So that's how they'll be doing. So let's say there's a geometric view. So run in the block 1, run in the block 2. Let's say in the block 1, that part we have that dark circle, we have the run on block 1, then block 2. This is the one, this is the one. This is the one that we are saying that contains the considered design in the figure. Note that block 1 contains the run 1 and the AB 1 and then AB, that is the one interaction effect, and that block 2 contains A and B. The contrast for the estimating the main effect are of AB like AR, that will be contrast of A will be AB, that we have to consider interaction effect, individual effect, minus of B, minus of first that run. Contrast of B, AB, that will be interaction effect, plus B in positive, then we have to subtract minus A, then B. So these contracts are unaffected by blocking, since the each contrast there is a 1 plus and 1 minus run from the each block. It's like it's just they are doing the complementing each other, because if we do the blocking, so they will take each and all parameter, but in the case of confounding, what they are doing, each contrast there is a 1 plus and then 1 minus sign, okay, for each block, from each block. So that is any difference between the block 1 and block 2 will cancel out. The contrast for the AB interaction will be AB, this will be positive, and then that interaction will be going to be individually they are going to remove it. Okay, so this thing I just try to explain that how the confounding going to work it out. I will show that that one table, that how we are doing for that, and this thing, like when you're doing designing the experiment for anything, so that will be the helpful for our course. It will be, but the assignment part it will be not that much helpful because they're already done. Now just change the 2 runs with the plus sign, AB and then block A are in block 1, and the 2 with the minus sign A and B in the block 2, and the block effect AB interaction are identical. So the AB is confounded with the blocks. So in the last, AB is going to confound it with the block itself. So just say this was the case for the 2 factor, like 2 blocks. Now we can do for the 3 factor. How that will go? So it will become cube. Earlier it was a square. Earlier it was a square. So 2 to the power 2 in the 4. Now we have a cube because of we have a 3 factor. So 2 to the power 8. 2 to the power 3, it becomes 8. So we'll be having 1 A, B, C. Then we'll be having interaction effect between the 2 AC, AB, and then BC, and then last it will be the ABC. Now the block 1 and then block 2. So I told In one block you have to keep 4. In the two case we have to keep at least 2. But in the case of 3 blocks, we have, total number of experiment we have 8, so we have to keep at least 4. So block 1 they get 1, and then AB, AC, BC, that's a two interaction effect. Block 2 AB, C, and then ABC. That ABC is going to be confounded. That ABC is going to confounded. Okay. How? Because just see, if ABC will going to confound, then it will going to reduce the number of runs. Because, and one more thing, in the last session I have told, when for the ABC that will be always I, that will be the identity, or that will be always positive only. That's the thing that will come when you are doing that. That's how they are going to reduce the number of experiment. So these are the all about the confounding and then blocking. Now we'll come to the design resolution. Can you someone read and then try to understand what is it exactly? I will. Just wait for 2 minutes. Huh? Okay. Thank you for the waiting. Design resolution. Let's say resolution 4 design. Why it not 1 came 2 or 3? So because if you see 2 to the power 1, 2 to the power 2, 2 to the power 3, that we have already discussed. We have that design matrix was there. Okay. So there is no main effect in the resolution 4 design. In this design, no main effect is allied with any other main effect or two-factor interaction, but two-factor interaction are allied with each other. Okay, and then that resolution 4, what will happen? 2 to the power 4 minus 1 design. So it will be allied with I is equal to A, B, C, D. So this is all about the resolution 4. For that, if you see that I will show you that table how that resolution 4, resolution 5, resolution 3 or 4 that going to be done. For the case of 5, in the design, the no main effect or two-factor interaction is allied with any other main effect or two-factor interaction, but the two-factor interaction is allied with the three-factor interaction. It's like a, so it's somewhere like in the 4 design, it will be the any main effect or two-factor interaction, but the two-factor interaction are allied with each other. In that case, they are going to allies with the two-factor interaction only, but with each other. But in the case of resolution 5 design, no main effect or two-factor interaction is allied with the any other main effect or two-factor interaction, and but the two-factor interaction initially they are not going to allied with the two-factor, but two-factor interaction are allied with the three-factor interaction. So 2 to the power 5 minus 1. So that I is equal to A, B, C, D, that is going to your allied. So 4 with the I is equal to A, B, C, D is of the resolution. 4, resolution 3 and 4 design are particularly useful in the factor screening experiment. It's like a why we are doing the resolution, that we are trying to screen the experiment, that whatever the variable that we need to require, that we have to take, other we have to eliminate it. So resolution 4 design provides very good information about the main effect and will provide the some information about the two-factor interaction also, that we'll see. Now the smaller fraction, you might have seen like it was the till we were taking the 2 to the power 4 minus 1, 2 to the power 5 minus 1, 2 to the power 6 minus 1, but let's say we'll be having some fraction that is a less than, although that 2 to the power k minus 1 design is the valuable in the reducing the number of runs required for an experiment. We frequently find that smaller fraction will provide almost the much useful information even at the greater economy. Okay. So in that case, so you have to, like in that case they are going to reduce the thing, but that is going to even greater economy also. But in general, what will happen? 2 to the power k design may be run in a 1 to the power 2 by fraction, 1 to the power 2 to the power p fraction called 2 to the power k minus p fraction factorial. So for 1 by 4 fraction is called 2 to the power k minus 2, and 2 to the power k minus 2 fractional factorial design, and 1 by 8 fraction is called 2 to the power k minus 3, or 1 to the power 1 by 16 fraction is called 2 to the power k minus 4 design. One question was there, I think in the 7th or 6th quiz. Let's say we have a 7 factorial, so how that is going to run out? So it was 8 minus 1, 1 by 16 by what there? What by 16? 1 by 8 was something question was there. In that you have to find out that number of experiment. So that's how, if it is 1 by 16, so it's a 2 to the power 4. So let's say we have a some sort of 6 factor are there. So 6 minus 4. So you have to run only 4 number of experiment. Let's say you have a number of factor 16 are there, and they are showing to run 1 by 32 fractional factorial design fraction. So what will happen? 1 by, or that will be 2 to the power k, or 2 to the power that k we have 16. So 1 by 32 will become 5, 2 to the power 16, 2 to the power 5, that's in power. So 2 to the power 6 minus 5, it becomes 2 to the power 11. So that much number you have to run the experiment. So that one question was somewhere related to this one, smaller fractions. So the concept of design resolution is a useful way to catalog fractional factorial design, and according to the alias pattern produced. Whenever we are going to do some fractional design, so in that what we are doing? We are doing some aliasing or confounding. Okay, so design of resolution 3, 4, 5 are particularly important, and that we can see resolution 3 design. In this design, no main effect are allied with any other main effect, but main effect are allied with the two-factor interaction, and two-factor interaction may be allied with each other. Let's say we have a B, C. So alliance will be A, B, C. So individual factor will be A, B, C, A, B, A, C, B, C. But there will be not A, B, C. Why? Because we are doing the confounding for that. So means, so no main effect allies with any other main effect. So means there is a main effect that not going to be, it's to be individual, but main effects are allied with the two-factor interaction, and two-factor interaction may be allied with each other also. So AB, AC, BC. So that's how it goes. So I is equal to ABC is the resolution 3. We usually employ a subscript Roman numeral to indicate design resolution, thus the 1/2 of the fraction. Whenever they will say I want to do the 1/2 fraction design, so literally they are saying 3 minus 1 design. So they have to run the experiment for the 4th time. Okay, so this was the resolution 3 design. Whenever they will say resolution 3 design, so they have to run number of experiment at the 4th time. Okay. Now we'll design the design generator. Let's say now in the aliasing what we were doing, we were having a 5 factor was there, so we were doing aliasing with the all multiplication A, B, C, D, E. But sometimes it might be some different will be there. So for that, how we are going to do the design generator? So selecting a design generator, in the foregoing example, we selected I is equal to A, B, C, D, or I is equal to B, C, D, F, because it was, we are having 6 and then 2 were like 1 by 4. we were doing experiment. So the generator to construct the to the power 6 minus 2 fractional factorial design. So we have to see from the table for a given number of factor, for a number of factor, let's k, and number of runs we wish to make. So that number of runs will be maybe that we are keeping in that. So we want to select the generator so that design has the highest possible resolution. We will try to keep that is according to the Montgomery that they have told, like we have to keep the highest possible resolution, so that we will get better effect of factor. That may be the main effect, or either that will go into interaction effect. Okay. So Montgomery present a set of design maximum resolution for 2 to the power k minus p design with the p is going to less than 10 factor. So that will be 10 minus that p. So that p can be a 1, 2, 3, 4, 5, 6, whatever you want, like that depends upon the number of factor. So according to the Montgomery John, that 2 to the power k to the power factorial design. So they are going to deal with like number of factor we have 3, resolution that is that resolution of 3. So number of run we have to do the 4. Okay. Okay, and we have the number of factor 4, and in that case resolution 4 case, so we have to run the experiment for the 8. So design generator will be having C is equal to AB, or either D is equal to ABC. So it's like a last term, that's not the aliasing, that will this is a design generator, that will be the last term. For the number of factor 5, that can be a 2, like maybe that we have to run for the 16 number of runs, or maybe the 8 number of runs. So for the case of E, that will be A, B, C, D, and for the D and E, it will become a two factor interaction. In the similar case, we have to do for the 6, 7, 8 till 10. So that is a possible design generator that we can produce. So this is the one table we need to follow it out. Let's say in some case we'll have 10 number of factors are there, or number of runs we want to reduce it. Number of runs we are keeping from this. So in that case, what are the possible design generator can be for the aliasing effect? Let's say we have a f is equal to a, b, c, d, e. So in that case, you will be having 32 number of runs you have to do. Now sometimes we'll say, okay, no, we'll not do for the 32, we want to do for the 16. So in that case, either you can go by this either two design, e is equal to abc or f is equal to bcd. If that two you need to follow it, so that two things will comes into the picture. In the third case, if you are doing with that 1 by 8 times fraction, so that will be the 8 number of runs A, B, A, C, B, C. In the similar way, you have to follow this one. So this is all about the confounding and that blocking concept. So now we will discuss about some sort of Plackett-Burnman design. So earlier we were discussing about that some factorial design and then fractional factorial design, or the full factorial design. So that Plackett-Burnman design, actually they are more or less dealing about multiple 4. Multiple 4 can be that 4 number of factor, or 8, either 12 number of experiment we can say. So actually that's for the good for the screening design, and then can study main effect at the 2 levels. So for design effect, so for that how we have to design. So if you see in that we are doing for the 4 number of factors, so we have to see about the 3, or either if you are doing the 8, so that will be 7, or at the 12, so that we have to do the 11. I will show you how. Let's say we have a 2 to the power 3. Actually, it should come 8 number of run. Okay. So now what we have to follow, like 8 column will be always negative. Let's say we have 12 run. So that's a 12 run will be the always negative. So in that case, that we have positive, and then so we have to just we'll see 3 here, then negative plus, then negative. In the second case, that will become here, like this it will go. Like this it will go. If we design the experiment like this, so it will be like this it should go. It's a diagonal step we can. So generating the column for the various Plackett designs are n is equal to 8 or either 12 or either 16 or either 20 or either 24, and we have to keep in mind this last row always will be the negative, and we have to go further proceed like this way only. And one more design of experiment is there, Latin square used to generate a Latin square. In that factor a, that coded values are inside the square, that will be -1, 0, +1, that depends upon the how we are coding. This is the factor C, then factor B. So there, it's somewhere, it's not the square design, but they are trying to take the interaction from the factor B and C and factor A that we have confounded inside itself. So based upon that, they are going to find out the main effect or either interaction effect. So in that response, this was all about the other design. Just for understanding where to use and all the thing. In the response surface method or design, what we are doing, it's a collection of mathematical and statistical technique that are useful for the modeling of first order design or maybe second order design. So analysis is the application where response of interest is influenced by the several variable and the objective is to optimize the response. So our objective will be we are going to optimize the response, but there will be several factors that are going to influence the. Let's say for the first order, what we are saying, y is equal to a plus bx. It's a linear design, or maybe second order. A plus bx square plus cx plus t. So now we have to do that, can be done by using some optimization method. If we want to say that I want to do the fitting of line, so you can use the least square method. So that response can be in any way, that may be the first order or the second order. So that you have to check it out, and then based upon that you have to, and then this least square method I will discuss once we'll start the regression method. So now we'll come to the regression model and then residual analysis. So when we have a residuals from 2k design, like 2 to the power k design, like k is the number of factor. So design the fitting a regression model to the data for the router experiment. The regression model is y is equal to b0 plus beta 1 x1 beta 2 x2 beta 1 2 x1 x2. So there is interaction effect again coming into the picture. So it's like a, so this will be your intercept. This is your coefficient. So that we need to find out. And when we are discussing about the regression, so before starting to the regression, we have to solve it out the Karl coefficient. Okay, correlation coefficient between actually this is the between two random variable x and y, usually denoted by r of x y. Or simply rxy is a numerical measure of a linear relationship between them and defined as rxy is equal to covariance of xy upon sigma x sigma y. Anyone know the formula for that covariance of x and y? Covariance of x and y. Covariance of x and y formula, we have sigma of x y by n minus sigma x by n sigma y by n, or we have some different formulas out there. 1 by n we can get x I minus x bar minus, not minus, it's summation of again y I minus y bar. So that is for sample, that's for population formula. I'll show you the formula here, like here. So covariance of x and y for the population, it will be the n, and for sample it will be the n minus 1. So can we do one problem? This problem, so we have to calculate the correlation coefficient for following height in inches and then father x and their son and y. Okay, So please calculate the correlation coefficient. We have x and y value. So we have to calculate the correlation coefficient value. Even we can get that what we can say, intercept also, or regression line also, slope also we can get it. First we'll try to find out the correlation coefficient. So we have a, we'll try to make a table x and y, 65, 66, 67, 67, 68, 69, 70, 72, 67, 68, 65, 68, 72, 72, 69, 71. Or one more thing I will say, you can get directly formula. Okay, so I will write the formula for R of xy directly, that covariance of xy, sigma xy. So we can write sigma of x minus x bar, sigma of y minus y bar by root under summation of x minus x bar to the whole square, summation of y minus y bar whole square. That is the one formula we have. So you can from here you can calculate the x and y and calculate the x bar also. Now we'll calculate x square, y square, xy. Okay. We'll have one more formula. I will write here also. N sigma xy minus sigma x sigma y, and n sigma of x square minus and you can for the same case of y. Okay, please do it this one. You can use any of the formula. I will use that last one what I wrote. So x square, anyone is trying, please just do it. I'll just wait for some 5 minutes. And you are free to use any other formulas also. There is no compulsion that whatever I wrote you have to use that formula, particular formula only. You can say the final answer also if anyone got. If anyone is ready with the answer, please say. Anyone is ready with the answer? Okay, so x square, if we get 65 square 4225, I will slowly start, and 66 will be the 4356. Let me see with the calculator, where is that? 67 square will get 4489, 4489. 68 square 4624, and 69 square will be 4761. 70 will be 4900. 72 will be 5184. 67 will be having 4489. 68 will be 4624. 65 4225. Again 68 will be 4624. 72 5184. 5184. 69 will be 4761. 71 will be 5041. And can anyone say about xy? 65 into 67. 4355. 4488. 4355. 45 46 45 56. 4896. 4968. 4830. 5112. Can anyone say about x bar also, or we have one formula directly? How many numbers we have? N is equal to 1 2 3 4 5 6 7 8. So we'll use R is equal to n of summation of xy minus summation of x into summation of y into n summation of x square minus summation of x square n summation of y square का sorry 8, and the summation of xy, how much will get? 3 7. Anyone is doing? Can you please tell? No one is doing. 3 8 1 3 2 3 7 0 to 8. Sigma y will get 5 5 2, and sigma x we have 5 4 4. So we will be going to multiply with 3 7 5 6 0 minus sigma x into sigma y 544 into 552 under root of 8 x square, summation of x square 3 7 minus sigma x square 544 square minus 8 into y square 38132 minus sigma y 552 whole square. Anyone got the answer? What the value of r? What is the value of r? Even you can use directly Excel also. If you have went through the lecture, you have seen that Excel formulas for that. Please, anyone say about R value? Point? Yeah. Anyone others? Point 6031. So now we'll start the regression, and then this is also regression part only, but this is the coefficient coefficient. One formula was there, and second part, this was the formula for that coefficient coefficient, spark one coefficient coefficient. Now we have y is equal to mx plus c. So formula for the m and c. So either two ways will be there, fitting a straight line. Usually what we are doing that y on x, usually what we are doing y on x. So y will be having formula y minus y bar, and that byx, or either we can say slope x minus x bar. So for that formula we will be having byx. It will be formula for r and sy by x. So sy we have a sigma x, but we say sigma x will be sigma y, and sx will be the sigma x. Sigma x formula that we have formula for sigma x and sigma y also. If we take for the sample, so sy will be y minus y bar by n minus 1 into whole square, x minus x bar whole square upon n minus 1. So this one for but you can say sy, sx and byx formula, the same formula that what we are using for the r. Okay, that we can use that n sigma xy minus sigma x sigma y, and that will be n sigma x square minus sigma x to the power whole square. So this is for y on x. In the question, if they have mentioned that our line is between y on x, so that formula you can use this one. Or if the question is not mentioning, so we have to use this one. If specifically they are saying x on y, x on y means y, instead of y minus y bar, it will be the x minus x bar. Byx not there, bxy will be there into y minus y bar. Okay. So this was so for the formula for the bxy, what will happen? N, that xy minus sigma x sigma y. Now instead of x, now it will be the y. Simple. And usually in our course, that is the line was that is already sitting on the y on x. So we'll use this formula and this formula. This is for slope. Okay. Now we'll take one more page and I will write some more formula for intercept and then the r square value. Okay. So we have that y is equal to mx plus c. To want to get c is equal to y minus mx, or either y minus mx bar. So that one will use that m formula will be having that slope formula that we have already. Okay. So that slope formula will be, we are going to use that one. Okay. That's what we are saying, m is equal to, or that pxy is equal to r sy by sx, that formula that I wrote in the last. So that intercept formula, this one is slope formula, and that r square determination. R square usually is what we are saying SSC by SST. Summation of sum of square of error, summation of square of like total. So for that formula we will be having 1 minus summation of y minus y, that cap will get from here, y is cap will get for mx plus c. So for all of x we have calculated the m, we have calculated the c, that will put for all x will get a 1 y value. So that y value we are going to put here, and for summation of total, that will be summation of square y minus y bar whole square. So this is the formula for r square. One more we have adjusted r square. For that we have to use the formula for r square is equal to 1 minus, okay, 1 minus SSE n minus 1 and SST n minus p. Here the p is the, here p will be the number of terms in the regression. Let's say we have a y is equal to mx plus c. So here p will be 2 and n will be the number of variable that we will be having in the question or data point. Number of terms will be the x and y. Okay. No, only x or only y, x and y. So if let's say some 10 10 12 12, so 1 2 3 like this it will go total. So this is all about the r square adjusted. And one more formula we have, the degree of freedom. Degree of freedom will be n minus p. Okay, degree of freedom will be having n minus p. Shall we do one question based upon this? We'll starting with finding out the slope, then intercept, then we'll find out the residual like error, SSE, and then SST, and then we'll find out the R square adjusted. So we have at this data point. Can we start for doing this one? Okay, so this is the data set we have, 10 number of data sets. We have the n, and p will be the always because we are going with a straight line. So please find out the slope, intercept, and r square adjusted, degree of freedom, SST, SSE. Please do it. I'll wait for some 10 minutes. We have the data set, statistic, and science. First one is 20, 23, 8, 29, 14, 12, 11, 21, 17, 18, and let's say this is the x and this is the y. Science one we have 20, 25, 11, 24, 23, 16, 12, 21, 22, 26. So in the first instance, please try to find out the x bar. X bar will be having summation of x by n. That summation of x will get somewhere 20, 20, 43, 51, 51, 29, 80, 40, 94, 106, 117, 17, then 138, 138, 155, and then 173. Sigma y will become 20, 25, 45, 56, 56, 24, 80, 103, 109, 131, 143, 143, 165 plus 26 is get 200. 173 by 10, 17.3, y bar is equal to, we'll get around somewhere 200 by 10 is equal to 20. Now we'll calculate the x minus x bar, y minus y bar. So we have 20 minus 17.3, that will be 2.7. You can use any formula, that I am using this formula, that second formula. And 5.7 minus 8, 9.3, 11.7 minus 3.3. What? Sorry, I can't hear properly. Can we take this one? Okay, that's a 20, na? Okay. Is it correct now? Okay. Summation how much coming? It's 172. Okay, 172. So it will become 170, 17.2. Okay, 17.2, so it will be 8. Okay. Try to find a way. Five point eight. 1.28 to 2, 11 minus 6.2, 20 minus 17.2, 20 minus 17.2 is 3.8, 17 minus 0.2, 18.8. Now this one will get 7.29. No. 20 minus 20 is equal to 0. 20 minus 20 is 0. 5 minus 9. 4. 3 minus 4 minus 8. And 1, 2, 6. We'll calculate x minus x bar whole square, y minus y bar whole square. Okay, so we'll have 2.8, 7.84, 5.7 square, 32.94, 9.2 square, 80, 11 point 139, 3.2, 10.24, 5.2, 27.04, 38.44, 3.8 square, 14.2. 1 2 3 4 5 6 7 8 9. 0.64. 0, 25, 81, 16, 9, 16, 64, 1, 2, 36. Now you can apply the formula for first will be the SY, root under y minus y bar whole square by n minus 1. X will be x minus x bar whole square n minus 1. Then R formula you can apply for sigma of x minus x bar y minus y bar root under summation of x minus x bar whole square summation of y minus y bar whole square. We will get some, how much the R value we are getting, anyone can say. Then we can apply for the M slope R and Sy by Sx. So first we have to get the R value. R value we are getting somewhere around 0.75 or 0.76. Anyone? How much for the slope? Okay. Okay, 5 point. Okay, 30. Okay, 6.4. Sorry. 6.4. Which one? Which one? Statistic 20. Somewhere I am getting wrong. It. We are getting somewhere y minus y square summation 252. Is it correct? Yeah. And then summation of x minus x bar square will get how much? Around 350. Exactly, I don't have the answer for all. 349.6, na? Okay. Now we can calculate this one also. X minus x bar, y minus y bar. Y minus y bar will be having 0. No. we should get y minus y bar, and then x minus x bar should be 0. And we have to one more cable we have to take, x minus x bar, y minus y bar, then we have to multiply this and this, it will become 0. It got very messy here. Can anyone say the answer for this, final answer? So you will be having the data like this. Okay. You have to calculate all the parameter from this. Which one? Which one? R. Sy or Sx. Okay. Okay, fine. We'll get, it should be somewhere 0.6 to 7 only, the slope will get. And intercept how much? 8.84. So now we have the value of m and then intercept. So we'll calculate the one more thing, we have to add it for getting r square. We have the formula for r square, 1 minus SE SST, 1 minus summation of y minus y cap whole square, summation of y minus y bar whole square. So we have to calculate the y cap from mx plus c. So for each m, so we'll get one more y. We have one y already, we have this one. So we'll get one more y by keeping m and x. M we have 0.64 plus x plus 8.84. So y bar 1 will get some value, y 2 will get some, sorry, 0.64 x plus 8.84. So for each value of x, we will get one y cap, y4 as y10 will get. So then after we have to calculate the y minus y bar. One column will again will come, y minus y cap. Then we have to get the summation of y minus y cap. So this value we have to calculate, and this value we already know. So we'll keep r square formula and we'll get the answer. For r square adjusted, we have to same technique, y minus y cap whole square, summation of y minus y bar whole square. Here it will be n minus 1, here it will be n minus p. So this is formula for r square adjusted, and then degree of freedom will be your n minus p. So we have n 10 minus 2, it will become 8. Okay. So this one is already SST, so we don't need to calculate. So we have already calculated, this is the SSE. Any doubt is there in this part? Okay, so we have one more question is there. A study is conducted involving 10 patient to investigate the relationship between the effect and patient age and their blood pressure. So we have again 10 observers are there. Same thing, nothing new. Now you have to find out the calculate the linear regression. It's like first you find out the m, then intercept, then we'll get a 1 ymx plus c. Same way r square adjusted, degree of freedom. This is only x and y value. This one I have taken, so I have taken in the printout. So it's no, it's like a it's just a multiplication. 35 into 112, it will get 3920. So it's already calculated. So now you can go ahead, or either you can use the last question formula we have used, exponential x bar, or either you can use this formula. Whatever you are comfortable with, that you can use the formula. In this case, slope formula will have n sigma of xy minus sigma x sigma y. This one is sigma x, sigma y, sigma x, sigma x square. This one already given. So just use the formula nx square minus sigma ka whole square. So you will get a 1 m slope value. Okay. Then you can calculate the intercept also. That will be your y bar minus m x bar. So you will get a 1 intercept value. And for this particular case, that you can use sigma x or sx, you can use the formula root under sigma x square by n minus sigma x whole square by n. Y you can use anyway, not required. Maybe you need to find out for that what we can say SST. For SST you have to go through that one only, y minus y bar whole square by n minus 1, or either you can use the n also, no issue with that. Sorry. How much you got for slope? It's 1.13 or 4. Okay, fine. And intercept will get around somewhere. How much we are getting? 85.06. 85.026. Is it correct? So we will have the equation y is equal to mx plus c. M we have 1.13. That is a x age is here, x plus 85.026. So regression coefficient, that slope is there saying indicate that as age increases by 1 year, the blood pressure will increase by 1.14 times. And in the case of intercept, we will say for at age 0, we will be having blood pressure of 85.06. It's like something that y is equal to mx plus c. So if the age is 0, so that m will keep, that will get cancelled out. So c will be 85.06. That's the interpretation we are saying. That's how we will say when there is a no age, like there is a age 0, so that much BP will be there. And when we will say like if the increment of age by 1 year, so there will be increment of, in the BP it will be 1.14 times, increase by 1.14. And R square value will get somewhere around 0.81 if you are calculating. Shall we go ahead or rather we'll wait for some time? Okay. So now we'll discuss about the control chart. Before that, I want to show that how we are doing the least square method. I'll just explain you a bit, not too much, but one example we'll take and then we'll do. Let's say we have a equations like y is equal to a plus bx. That will be the fit of regression line using least square method. So what we have to do first summation y is equal to na plus, okay, and then that will become sigma x plus sigma x square. Now solve for these two equation. Two unknown a and b, get the value of a and b, you will get the answer for that. Let's say we have this data set. This data set we have already calculated. Take this data set. I will take this data set only. We can solve the problem here also. Sigma y we know, sigma y we have 1410. 1410 is equal to n. How much n we have? 10. A plus b we don't know. Sigma x we know 491. Okay. Sigma xy, sigma of xy 7566 plus a we don't know. Sigma x we know. How much? 491 plus b summation of x square we know. Can anyone solve and then say the value of a and b? One equation, two equation, what is the value of a, what is the value of b? Whether we are getting same or not. We'll check with that. I will solve. Let me try with that. Question two unknown. A1 is I have a 10, 491, 1410, A2, 491, 265157. We'll get we are getting same now. We'll get the value of a, that is the intercept we have 85.04, and we'll get slope value 1.139. So you will do, that's the way that you can do. Let's say we have an equation of a plus b x square plus cx. Okay, what you do? First you take the summation n a plus b summation of sigma s square plus c summation of x square. because we have no, it should be without square. This is the equation first, sigma xy, that will become a summation of x, b summation of x square plus c summation of, no, this is the x square, no, it is x cube. Now this is the equation 2. Now sigma x square y, a sigma x square plus b sigma x power 4 c x to 3, it will become equation 3. So we have a 3 unknown, 3 equations, so we'll get the value of a, b, c. So that's what we are saying, the fitting of regression line. So this is the one listed square method. So this is the for one variable, 2 variable, then 3. Let's say we have a equations of e to the power a to the power b x, something that logarithmic will be there. Okay, so what we can do, we have one equations will be there, like just 1 minute, what is the exact equation, I'll see. Y is equal to a b to the power x. Now what we'll do, we will take logarithmic log of y plus log of a plus log of b to the power x. That will become log y log a plus x log b. What we'll do, now we are going to replace with the capital Y. Y is equal to a plus b x. So what is the value of a? A will be log a. Whatever the value will come, a, and then we are going to put the a is equal to anti-log, a is equal to anti-log a. So what is the value of b? So log b. So b will become, small will become anti-log of b. So that become our first one. So that similar way you can do it. Okay, so this is a method of least square method actually. Now we will go for the control chart. Anyone have the idea what is the control chart actually? Control chart. So control chart is a statistical tool usually used for distinguish between the variation in process. So actually they are going to distinguish between variation in a process resulting from the common causes and variation resulting from the special cause. It's like that they are going to differentiate due to the variation in any process. That may be the common cause, or either maybe that will abruptly change. And it presents a graphic display of process stability or instability over a time. It will show in terms of center line, upper limit, lower control limit, that this is the we have center line, and they will show this type like data. It's like some sort of like this also. So this is the graph that control chart we are saying. Now we have to define, okay, what is the upper control limit, what is the lower control limit, how much the times the data is going beyond of upper control limit, or either lower of below of the lower control limit. Based upon that we have to decide which control chart we have to use. So one goal of using a control chart is to achieve and maintain the process of stability. Let's say you will be having fluctuations are too much, so that process is not stable. So what we have to do, we have to stabilize the that one. Or control chart is usually used to achieve and maintain the process stability. What is the that is the process stability? Process stability is defined as a state in which a process has displayed a certain degree of consistency. It's like they will show a degree of consistency in the past and is expected to continue. Let's say they are showing this, that one value is coming 1, second one will become 1.1, maybe 1.01, or maybe maybe 0.999. So it's like a degree of consistency in the past and then expected to continue to do in the same in future. So this consistency is characterized by the stream of data falling within the control limit based on the plus or minus 3 standard deviation, 3 sigma. Based upon the thing, like earlier we have to 2 sigma, 3 sigma, but usually we'll go for the 3 sigma design, 3 sigma deviation. We'll check, we have center line, then upper control limit will take 3 sigma, lower control limit minus 3 sigma. Based upon that we are going to say whether the characteristic stream of data falling within the control limit based upon the plus minus 3 sigma. So that means if any of the data that is falling, their range is minus 3 sigma plus 3 sigma, they are falling in between. So that will say that is the process stability or stable process will say. So control limit represent the limit of variation that should be expected from a process in a state of statistic control. So it's like a, this is, let's say, lower control limit, this is the upper control limit. So this is the range actually, or variation we will say. It's actually a variation. So why should team use control chart? To monitor the process variation over a time. Let's say if this is a time processing, so we'll see how much ups and down, maybe like this or either like this, maybe how the things are changing. Differentiate between the special cause and then common cause of variation. If we change any parameter, that will be the special cause or maybe the common cause. Based upon that, how you will do. Then assess the effectiveness of the change. Then after we, based upon that, we can see the effectiveness of the change also. Communicate the process performance also. So this is why we should use the control chart. What are the type of the control chart? So first one is the based upon the attribute, then variable. Anyone can say about that there are two main character control chart. Those are the display attribute data, those display variable data. Anyone say please the difference between the variable and attribute? What is the difference between the variable and attribute? Anyone have the idea? Variable we are saying that it's a quantifiable, like we can count, and that one we are saying non-countable. Maybe the yes or no, maybe the accept or reject, or maybe we'll say confirming or either non-confirming. The attribute data, this category of control chart display data that result from the counting the number of occurrence or item in a single category of a similar item or occurrence. Means the count data may be the expressed as a pass or fail, yes or no, presence or absence of the defect, maybe that accept and reject. So that is attribute we are saying. We are not saying in terms of how much percentage of change is getting changed, how much change is coming. That we are not saying. So another one we have the variable data. Variable data that we can actually display the things that how much changes are coming actually. The category of the control chart display values resulting from the measurement of the continuous variable. Example of variable data like time elapse or temperature, maybe the radiation dose, maybe the drug dose, but that thing like that we can count it. So can anyone say like what are the control chart is there? So if we say for that control chart for the variable, that we have x bar chart or r bar chart, and the control chart for attribute will be having u chart or either c chart or maybe the p chart or either np chart. So these are chart we are saying for that. Or if we say about the in general, so upper control limit will be having x bar plus 3 sigma by n, or lower control limit will be having x bar minus 3 sigma by n. So usually that is used for x bar or this one. For C and then P or either P chart or NP chart will be having different formula. Shall I show you some just brief, or either will stop the session for today? Okay, I will just show you in one textbook I have. I will just show you. Okay. and this one expert also I'll show you for that what you can say P chart and then NP chart also. What is the formula for that? Let's say we have a P chart. Three note 7. So for that we have the formula for upper control limit. This is the upper control limit we have, the P plus 3 into P into 1 minus P by N, and central line will be the P. Lower control limit will be the P minus. It's a P, what is that? That is a central line value. Okay, so generally the formula will be the 3 that's x bar plus minus 3 sigma. So in that case, so here that is a P bar, that is we will be having that is that center line, then 3 into sigma value will be the P bar into 1 minus P bar by N, and then lower control limit, that's the only change, that will minus. Let's say we have a one example is there. So in that P bar value they have given already, that we have to find out. There is some datas are there, based upon the data we have to find out, and some non-conforming and then sample, that total they have 30s are there, number of non-conforming cans, number of non-conforming fraction of that. So we can get P bar from here. We'll take the average of all this 0.4, 0.3, 0.16, this, and then we'll get the P bar, and this is a number actually 370. So total we have Mn 30 into 50, and we'll calculate the upper limit and then lower control limit. Based upon that they have to interpret here. So this is all about the P chart. So you can just see the formula for this one. For P chart, this control chart often called the P chart. Let's say I will show you for the NP chart. What is the formula for? So there is one additional term will come coming into the picture. That is NP chart. For that we have the formula upper control limit NP plus 3 into root under NP into 1 minus P. Then center line will be having NP, and then lower control limit that will be minus of, instead of plus will be having minus. Let's say we have a setup of a NP control chart, just to concentrate on, and then they have given P bar and then N, so we can directly use the formula. Same last one was there. Then we have a C chart and U chart, that will not, and I will be saying that which one we can apply. That one 346. The guideline for the implementing the control chart. So we have to, in the statistical process control, we have to say determining which process characterized to control. Then determine where the chart should be implemented in the process. We have to see that problem statement only where we are going to, what are the process that characteristic to control. Maybe what are the where we have to apply. Choosing the proper type of the control chart. Okay. And for choosing the proper type of control chart for X and R chart, considering using variable control chart in this situation. So if a process is new product is being manufactured by existing process, in that case you can apply for the X bar and then R. The process has been in operation for some time, like the process already was in process, but it is chronically in trouble or unable to hold a specified tolerance. In that case you can use the X bar and the R bar chart. And the same way, destructive testing, it is desirable to reduce the acceptance sampling in that case, or there may be a very tight specification or overlapping assembly tolerance. So you can see whenever the questions are there, based upon that, if you see this 10 some parameter, so you can apply for the X bar or R chart. For attribute chart, operator can control the assignable cows. It is necessary to reduce the process fallout. Means it's not the terms we are saying in the changing. We are saying that what are the cause? Maybe that one will be the defect coming or not coming, or maybe the process control is necessary but measurement data cannot be obtained. In that case, you can use the attribute chart. Okay, or that a historical summary of the process performance is necessary. Attribute control charts such as P chart or C chart, U chart are very effective for the summarizing information about the process for the management review. It's not about the quantifiable. And remember that attribute chart are generally inferior to the chart for the variable. It's not good as compared to the control chart for the variable, because what's happening, X bar or R chart, in that case they will give the superior result in as compared to the inferior, that attribute chart. So try to always use X bar or either R or either S chart whenever possible. Okay, so this is all about that control chart. Anyone have the doubt, you can ask. Otherwise, we'll discuss in the maybe next session on Sunday. Okay. Just to wait a minute, I'll check the PPT. Week, okay, week 2. Okay, fine. In that, okay, two of them will get the over. No, actually, this question is for normal distribution, na? Okay. 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 This thing I will upload the answer in that drive folder, or maybe the next session, huh? Okay. Anyone? So shall we? Uh-huh. Actually, that's not confirmed. That will be communicated by mail. I have to confirm with them. Yeah, it's a 21, 22 something, 22 or 24. Okay, 24. So, uh-huh. Okay, okay. Just I will note down. Which one you want to elaborate? Okay, how to take the Z value, no? Okay. Okay, fine. If the session will be there, then I'll do. Otherwise, I'll maybe supplementary material I'll keep in. If the session will be not there on the Sunday, so I'll keep some supplementary material there. Okay, so shall we wind up? Session was how was that? Can anyone rate it? Okay, okay, okay. Thank you. Okay, thank you. Thank you so much, everyone.